The potential of quantum technology is enormous, but there is a huge challenge facing the industry.
The main challenge is scaling the number of qubits, so to say the size of the computational space.
Right now, the largest single neutral atom-based quantum processing unit, QPU, has thousands of qubits.
However, to achieve the practical utility scale, you need millions of qubits in a single module.
So the real value delivery of quantum technology is hindered by the progress of hardware.
Now, one of the most promising direction is networking multiple QPUs.
NanoQT の答えは小さい QPU 同士をつないで一つの大きなネットワーク型の量子コンピューターとして使うという。
For the quantum computer, it's very difficult to connect, unlike the classical computer.
理由は量子情報はすごく壊れやすくて、かつ複製ができないっていう。
So you need to have a channel that's quantum, and that's the hard bit.
The mission of NanoQT is to develop a foundation for quantum networking in order to solve this massive scalability issue.
Our goal is to develop scalable quantum interconnect devices and also develop the architecture that can scale up to the utility scale quantum computing devices. Our technology is based on the fundamental physics called cavity quantum electrodynamics. Cavity QED is a study of how single atom and single photon interact inside the cavity at the single quantum level.
So the photon will resonate within the cavity and then increase the time that it could interact with the atom.
So quantum information is very fragile, but cavity QED allows us to interact the photon and the atom in a very controllable way.
The challenge is how to develop an ideal cavity for quantum networking, and our solution is using optical fiber.
We choose optical fiber as foundation because it's well known, it's commercialized, and it has very low loss for a long distance transmission.
QPU をつなげるって時に、そのすでに性能の高い光ファイバーに QPU がシームレスにつながってほしいと。
So we have a proprietary technology to manufacture a device called nanofiber cavity.
So we engineer our own nanofibers by tapering them down to 500 nanometers.
In this way, the light propagates this tiny cylinder. However, majority of the energy propagate outside. So in this way, even if you trap atom outside this waveguide, we can induce a strong interaction between photon and atoms.
さらにこのナノファイバーを共振器にするためにファイバーの中にファイバーブラックグレーティングというミラーを書き込みます。
それによってファイバーを通る光がその鏡を跳ね返って何往復もして光と原子が強く結合できるっていう強みがあります。
To minimize errors and latencies, we have to take QPU-centric approach so that our quantum interconnect device is compatible with QPUs.
Most of the interconnect providers focus on off-unit devices, but our approach is completely different. Our interconnect is directly sit inside the QPU and operating as an on-unit interconnect.
With this technology, we could also do long-distance quantum communication.
Because our interconnect operates as a quantum repeater.
So quantum interconnect not only contribute to the computation, but also the communication and furthermore sensing applications. This will open up a totally different field in physics, engineering, and industry.
This is the missing link from taking quantum computer in the lab to the quantum computer in the real world.
We are transforming how people think about quantum networking.
NanoQT のナノファイバーキャビティっていうのが世界中にこうあって、でそれがもう日々実際にネットワークするために使われていると、それは本当に自分にとっても夢になります。
So it would be really exciting for me to say in the future to my family and friends that I was working on this technology that transformed the world, and now it works because of our team and our efforts.
It's for me like a once in a lifetime chance to bring quantum computer to the world.
それが実際できると思うとやっぱりワクワクします。
Breakthrough happens when we establish connection. I believe the same thing will happen to quantum computers.